All right. Let's get it going. Actually, wait a second here. Oh no, hold on, there's some. Alright, we're back. Sorry about it. Alright. We are live in the Discord, and we are answering questions. Okay. So, if 144 grams of carbon dioxide gas is produced in 1 minute during a chemical reaction, okay, so I'm seeing a couple things here just to pick out mass, and I might even call that mass of CO2, and it's produced in, okay, let's just call that time. I don't know what other times are going to be, but let's just call that 1 minute. During a chemical reaction. Calculate the average rate of reaction. Okay, so this is what we're asked for. So the rate of reaction average. That's kind of what we're asked for. And we're asked for it in terms of moles of CO2 per second. Okay. Whoa. Excuse me. Okay. So we're given these. And we're asked this. Boom. Okay, so one part of this is just about the translation, yeah? Defeating the translation boss. Okay. Okay, just checking the stream health, sorry. Okay. So then how do we get the rate of reaction in moles of CO2 per second? Well, we're told basically 144 grams of CO2 in 1 minute. And we're asked for moles of CO2 in 1 second, right? So we have something pretty close in terms of some, measurement of CO2 over time, right? So now it's just about unit conversion. Okay, so the way we can do this is we can actually use these as a target. So, let's not do that. Okay. So, if I have minutes, I want to get rid of minutes, and I want to multiply it not by anything that's not 1. So I want this to be basically 1 over 1, right? But it could also be 7 over 7, right? For me, I want it to be some measurement of minutes, so 1 minute on the top, so that it cancels with this minute. But then that fraction has to be 1. So I'm going to turn it into the amount of seconds that I want, because 60 seconds is 1 minute, so that's technically a fraction of 1. So it's cheating, but it's not what we need to do. Okay, so then minutes cancel, and now we have the right unit on the bottom. So now it's just about converting grams into moles, and if you know anything about this stuff, then that's a formula you should be familiar with. So let's do it. Let's just do this multiplication. So it's really just 144 over 60, and that will be grams of CO2 per second. And so that is what? 144 divided by 60, so it should be like a little bit more than 2. If I screw this up by typing it in wrong, I might get something funky, like 24. But I know it's a little more than 2, so I'm good. Okay, so now it's just really about 2.4 grams. How much is that in moles, right? Well, that depends on the grams per mole of CO2. So the CO2 grams per mole is what we call the molecular mass of CO2. And this just comes from the mass of carbon plus the mass of 2 oxygens. So the mass of, so this is actually where the unit gram comes from, okay? The mass of a carbon is 12 grams per mole. And the mass of an oxygen is 16 grams per mole, but there is 2 of them. So we add those 2 together. And what do we get? Okay. So we should get what? 2 times 16, 32 plus 12, so 44. No. 44 grams per mole for a CO2 molecule. Okay. Okay. Sorry about that. Okay. So, okay, so this is kind of like a price. If you think of this, this is kind of like a price tag, okay? So this is sort of like saying that this costs $44 per dozen. CO2 molecules. They cost $44 a dozen, yeah? And so we have here 2.4 grams, $2.4 worth. So do we have a full dozen? Not even close, right? We don't, like, because that would be $44. So we have like $2, so it's like, what, like 1/20th of this amount, or a little less? So 1/20th is like 5%, so it should be a little less than 5%, right? And a dozen, well, a dozen is like a group of 12, right? It's a way to say groups of 12. It doesn't have any units, not like grams or whatever. And that's the same thing with moles. Moles is just like a molecular version of dozen. It's actually like 1.6 septillion, I think. Or about, no, 0.6 of a septillion. Yeah? So it's almost a septillion. Okay? It's just a huge amount. It's just a big number. Okay? Okay, so we should be able to say it looks like 2.4 divided by 44. And the way we do this is the same way we did this sort of unit cancellation here. What we want is to get rid of the grams of CO2, and we want to turn that into moles of CO2 up top, so that this one, come on now, so that this one cancels, and I'm left with just moles. Don't do that to me. Alright. And so, okay, so what do we have in terms of grams per mole? It's 44 grams per 1 mole. Right? So we'll have to divide by 44. The value we get there is 0.0545454545. So let's just say 55. Yeah? Moles of CO2 per second. And that's our answer. Okay. So this is just a unit conversion trick, right? It's just a unit conversion trick. Okay. Okay, so let's just sort of say that this all here and there, that is all what contributed to the molecular mass. Right, okay, so let's just do some rearranging. Boom. And a little bit of boom. Okay, so let's just say that this is the molecular mass of CO2. Okay, another way we could do this is we could just say that this is 2.4 grams, right? That is a mass. The molecular mass is 44 grams per mole, and we want to know the number of moles, right? So the equation is, well, it really looks like this, and over, sorry, all the way around, grams per mole, right? So what do we want to know? We want to know N. So that's little m over big M, and so that's why we did 2.4 grams divided by 44 grams per mole. The moles get flung up to the top. And the grams cancel. And we get the same value. Okay? So this is another method. Using kind of, you know, a little bit more rigid formulas. And we end up getting the same value. Okay? And we're really just taking the grams there of CO2 and, you know, putting it back in with the seconds at the end here. Right? The mole answer that we get. So this is 0.055 moles, and then we throw that in. Okay. So let's just put that in its proper border. Boom. Boom. Alright. Cool. So the question... answer. Okay. Cool. Okay. Let's do another one. We got anyone here yet? Hey. No. Well, I always said, you know, that's what my uncle told me when I was young. And I've just always stuck with that. Alright. Let's do this one. It's dirty. Boom. Alright. Okay. We're asked the variance, and let's actually crank you down a bit. Beautiful. Okay. We're asked for the variance and standard deviation of the following group of numbers. All right. So actually, sorry, let me just pull my chat. All right. Ah, yes, Constant Frank. Thank you. Thank you for your contribution. So, determine the variance and standard deviation of the following group of numbers. Okay, so what we're asked to do here is basically the variance is sort of how much jiggle is there in these numbers. So, this is a question that you sort of have an intuition for. So, if I gave you numbers like this, how much this varies versus how much this varies is very easy to say. Yeah, it's very easy to compare, right? The bottom one goes across a great amount of numbers, right? So what matters is how much they're going to shake, and this is something we have an intuition for. Now let's sort of like do the math of it. What we're going to do is compare it to sort of the average, the middle number, and how far away are you from the middle number, right? Because numbers that don't have a lot of variance will all hover around their average really close. And numbers that have the same average but have a lot of variance will bounce way further away on maybe on either side equally so that they land at the same mean, at the same average, right? So let's do this. Let's calculate the mean for each of these. So the way we're going to do that is we're just going to sum them up, right? Sum each up. X is kind of like each of them. N is the number of them, right? So sum each of them up and divide by the number of them, right? Okay, so then -1 plus 2, that's just 1, plus 10 plus 21 plus 27 plus 38 plus 50 is 147. So that's the sum of them. Divided by 1, 2, 3, 4, 5, 6, 7. Okay, so the average is 21. So the 21 is kind of the middle, right? So the mean is 21. The middle, the average is 21. Okay? And what about for this? So let's do the same thing for these two. And what do we get? So this is negative 20 plus 30 plus 0. That's just 10. Plus 3,000 plus 176173128. Divided by, how many are there? There's 1, 2, 3, 4, 5. Okay. So wait, 176176. Oh, interesting. 138. Okay. Whoa, 138 is half of 76 too. Interesting. Anyway, divided by 5, right? And so the average here is 35227.6 because this number is so huge, right? Okay. So that happens, right? Well, the question is, how far away are each of them from the mean, right? Well, these are only really like that one is kind of far away and that one's far away, but they're the two farthest away. But this one is only 29 away and this one is, 22 away. Negative 20 away from this one and 0 away from this one and 30 away from this one and even 3,000 away from this one are way more than this one. So that's variance. What we're sort of weakly analyzing there is variance. Let's get closer to the answer. So what we're going to do is we're going to take this mean, right? So for each of them, let's just purify. We have two sets of numbers, okay? One that has a mean of 21 and an n value of 7, right? And the other one has a mean of 3523527. Okay, let's just say, okay, 0.6. I'm fine with that. And B, there's only, get out of there. There's only 5 of them, right? Okay. So, well, what do we do with this? Now, the standard deviation is going to come from this. What we're going to need to do is with each one of them, we're going to compare it to the mean. Okay? So, let's do this. Let's make a little table, okay, for this one, and a little table for this one. Okay? And so, it's -1, 2, 10, 21, 27, 38, and 50. Okay. So what we're going to need to examine, this is x. What we want to look at is sort of, mu minus x, or x minus mu. It actually doesn't matter because what we're going to do next is square whatever we have here. Okay? So let's just sort of like take even the absolute value, just sort of how far away is it? Okay? And then we'll square that thing. Okay? Okay. So first, each one of them from 21. So this is 22 away. This is 19 away. This is 11. This is exactly on it. This is 6 away. This is, what, 17 away. And this we said was 29 away. Right? Okay, so that's how much each one varies. Okay. Let's keep going here. So what we're doing... okay, wait. So now let's square each of them. Okay. So 22 squared is 484. And then 19 squared is 361. And 11 squared is 121, and 0 squared is 0, and 6 squared is 36, and 17 squared is 289, 29 squared is 841. Okay. So the reason we squared is so that we don't have to worry about these being positive or negative, right? We could take the absolute value, but in a sense, that's what we're going to do. This is the same as taking the absolute value. Right? This just makes whatever number you have positive. Okay? So that's what we're going to do. But first, we're going to average. So we're going to actually sum these up. So the sum of mu, or we actually, I think, write it this way. X minus mu squared. So what will the sum of all of these be, right? That's what this will be. Okay. So what is it? Let's figure it out. Let's sum all these up. So 841 plus 289 plus 36 plus 0 plus 121 plus 361 plus 484. Boom. 2132. Okay, so that is the sum of all of these numbers here, which are the squareds of all of these numbers here, right, for each one. And these numbers come from how far away each number in our list is from the average. We found the average to be 21. Okay. Okay, so now we're going to take this thing here, x minus mu squared, and we're going to divide by the number of, so I'm just going to use n here. We're going to divide by however many there are. We're going to take the average kind of distance away. Okay, so let's do that. My camera here keeps having trouble. Let me just adjust here. This way. Okay. And then also the filter, croppery. I think we can just reduce the graph on both sides. Sorry, folks. Just adjust, you know, production quality. Alright, we're in. So, okay, so we're going to take the average of all of these things, okay? And this is actually what we call the variance, okay? So, divide that by, for us, 7. And so we get 304.57. Okay, and the standard deviation is just the square root of that. Okay, so the square root of the variance, which is the square root of 304.57, which is 17.45, baby. Okay, and so this is sort of like the average, you know, variation each number is from the mean, from the average, right? If everybody kind of like does about the same and it has the same average as people doing crazy amounts different, right? Well, that's what variance and standard deviation are used to measure, because the mean is the same, so you can't tell that much from it, the mean, right? Okay, boom. So variance is this, and standard deviation is this. Okay, awesome. And just as a little note, this means the mean, generally. Okay, and usually the mean of the sample, but we'll stop there. Okay, awesome. Let's keep it going, bro. Let's keep it going. Let's keep it going, bro. Let's keep it moving. If you got your own questions, submit them. You can put them in the Discord. And I'll do them today, tomorrow, next week, whenever. What do we want? Let's do these. These are interesting. Boom, baby. Okay. This needs to be adjusted. Boom. Alright. Okay, we're almost there, folks. Boom. Alright, what type of macromolecules are each of the following? What role does it play in the cell? Okay. So, let's call this A. Yeah, let's just black these out here for a second. And let's call that A and this B. Okay. So what role does it play in the cell? But first, what type of macromolecule are these? Okay. So let's do this in red. Okay, so we see nitrogens. We see a double ring. Yeah? Nitrogen's in those rings, right? This is a nitrogen base in DNA or RNA. Okay? So this is called a nitrogen base. It's a part of a nucleotide. In DNA and RNA. So that's kind of part of what role does it play, right? But we'll expand on that too. Okay. This is an oxygen-containing single carbon ring. Look at all the other members are carbon, but the oxygen's in there, right? And it's a 4 or 5 or a 6, and there's just a bunch of carbons with oxygens and hydrogens. No nitrogens, right? This is glucose. Yeah? This is the mark of glucose. Okay? This is the mark of glucose. Or not necessarily glucose, okay? This might not be able to easily say glucose, okay? And is this glucose? Yeah, I believe it is. Or it might be actually... Yeah, this is... No, this is glucose. There's... No, 4. Oh, yeah, no, this isn't glucose. Because there's 2 carbons on either side. But this is a sugar. Okay? So... or what we call a monosaccharide. Monosaccharide means there's just one of these, okay? So a disaccharide means there's two of them. A trisaccharide means there's three. A polysaccharide means there's many. Starch, things like wood and cellulose, those are all, well, I don't know about wood, but cellulose, those are all just long chains of sugar. Okay, some of them we can eat, like starch, and some of them we can't, like cellulose. We can't eat paper. Paper is cellulose. Vosh, thank you for your message. Vomong, I agree. You know, but just when are the people going to wake up and realize it, right? All right. All right. Let's do it. What role does it play in the cell? Okay, so we'll get there, but for now, let's just say that we're answering A in red here. Okay, so let's maybe do this. Okay, so this here, this is even kind of highlighted, right? The 4 chain there, right? And then there's a little kind of tail, right? This is the mark of a steroid. The 4 rings connected, that's the mark of a steroid. And then the extra like oxygens and carbons and hydrogens, those are the things, those are the difference between estrogen steroid, cholesterol, right? So this is actually, I think, yeah, we actually call this a sterol, right? A sterol group. But it's cholesterol, it's testosterone, it's estrogen, it's progesterone, it's all these things, okay? They're all in this steroid group. They all kind of like look pretty similar, okay? Okay, so this is what we call a what am I writing in red here? We call this a triglyceride. Right? Is that right? Let's just look it up. You know, everybody gets their sort of confidence rocked. Yeah, triglyceride. All right, awesome. So we have three lipids, right? And they have their own sort of like acid tail that can react with the glycose here, right? Oh, is that, what is it called again? Glycogen? Oh my god. Oh my god. Never doing this in a while. Yeah. Boom. Yeah, glycerol. Right, so that's our glycerol with our lipid tails. And so this is a triglyceride. Okay, something that we see, and maybe I'll just kind of highlight this in purple. Okay, those are the two different sections, but together it's a triglyceride. There's 3 of them. Okay, and it's on a glycerol. Okay, so the question of what role do they play? Okay, let's maybe do this in green. The nitrogen base. The nitrogen base is in RNA and DNA, right? So let's maybe just do this. 1, 2, 3, 4. There's 1. The nitrogen base, it's in RNA and DNA, right? Which is all about, you know, genetic messages. Genetic base pairs. Right, that store info. Crazy system that our cells have come up with a way to long-term store information in molecules, okay, and be able to go back and get them and reproduce it and all this stuff with little to no error, okay. Crazy. And the way that they do it is these things bonded kind of together. This is one of those A, G, T, and C, and U type bases. Okay. For two, so sugars, right? So this is, we eat it, right? Like glucose, but also energy storage, right? Like in plants. And we even store this, in our livers in long-term sort of chains of sugar so that we can quickly activate energy. Okay. Sterols, 3. Those things are usually used for hormones. Okay, so hormones like testosterone, estrogen, cholesterol, aldosterone, which controls water and other things. These are all sterol based. They're all they all look very, very similar. Okay, so that's what they're, and cholesterol has a role in the cellular membrane. Okay, so plus cellular membrane. Every cell has some cholesterol just floating around in it. Okay. Okay, so triglycerides are our last one here, and they, maybe we just do this. Come on, mate. Alright. Boom. Okay, cool. So, number 4, so this is a triglyceride. This is more long-term energy storage, okay? So this is like fats. This is how we store energy as fats. So these are sort of like fats for insulation and long-term energy storage. And we use them for a few other things, like this is actually the base of a phospholipid bilayer, right? Ah, Shirley. Oh my gosh, thank you. I almost forgot. Vamong. What was I thinking? Thank you. Alright, boom. We're done. Next one. I hit you with the next one. Doing the gauntlet. Alright, this is the last one left. Get rid of the box. We got 2 questions here. One's math, one's physics. If you've got any input, give it to me now. Forever hold your peace. Come on, mate. Let's do your homework. Do this. Boom. Alright. Let's do it. Okay, a triangle has vertices at P, Q, and R. Okay, let's see if we can actually draw this semi-decently. So let's see, 6, 7 is the biggest, so let's kind of go to like 8. Okay. Wait, in the X, yeah, 6. Okay, so let's just go to 8 in each. And then we'll cut it in half and cut it in half again. And cut it in half, cut it in half again. Cut it in half, cut it in half again. Cut it in half, cut it in half again, cut it in half again. Okay. 4, 4, 4, 4. Beautiful. Okay. So now P is at -2, 7. So -2 is the X. So let's go in the X. That's the horizontal. So let's go -2 here. And then 7 up. So we're in between those two. So that's P. Okay. And then we have Q, which is -4. Oh, this is, yeah, we didn't label this properly. This is -4. This is -8. Okay. So -4 and then just 2. So that's there. And then the third point is 6 and -2, which is way over here. 6 and -2 is here. Okay. So those are my 3 points. And so wait, let me just... Oh. Okay. So that point is 6, -2. This point is -4, 2. This point is -2, 7. Okay. So let's get some lines going between these folks. 1. 2. 3. All right. Beautiful. Okay. So that's our triangle, right? Okay. Prove that it's a right angle triangle. Okay. Prove that the circumcenter is at the midpoint of the hypotenuse. Ooh, okay. So we might have to talk about circumcenter, right? But for now, let's prove that it's a right angle triangle. So we could probably see where it's a right angle triangle, right? Now that we've drawn it. Might have been harder to see before, so that's one advantage of drawing it. That's for sure going to be the spot where we're going to, you know, kind of, that's the question, right? So let's do it. So we need to look at the line that comes from QP and the line that comes from QR and ask if those two meet at a right angle, right? So is QP perpendicular to QR, right? And that can be answered if we look at the slopes being negative reciprocals, right? That was our test for that, negative reciprocal. So let's look at the slope. So the slope of QP, is it equal to -1 over the slope of QR? So what we just need to do then is to find the slope of each of these, okay? So let's call that actually MQP. Okay. So the slope is M. And we're asking about MQR. Okay. And is it equal to 1 over right? So let's just solve it. So M of QP and M of QR. By solve it, I mean solve that equation. What we need for that equation are MQP and MQR. MQP is the slope of the line connecting Q and R, P, and the exact same thing, but for Q and R. There's one line of difference between those two. Okay? So, the slope connecting them, well, that's something that we can calculate. Remember, that's delta y over delta x, and so that's y2 minus y1 over x2 minus x1, and we can do that for each of them. So let's do that. And so what do we get? So 2 and 1 is just, it doesn't matter. It doesn't matter who we make 2, who we make 1, which is nice. Okay, so a lot of the times in math, if you come to a decision, it's worth it just to make one of them and know that if you get something wrong, like you prove that 2 is equal to 3, go back and make the other decision. It's better to just choose something and know that it's wrong than to deliberate on a choice. Okay? If you know that there are 2 possible pathways, at least you have pathways, so walk them. Okay? Okay, so let's do y2. So I'm going to do q and p. So I'm going to make p, I'm going to make that my 2. Okay? So that's going to be 7 minus 2 over -2 minus -4. So I get 5 over -2 minus -4 is -2 plus 4. So that's 2. So it's 5 over 2. Okay, let's see between Q and R. So that I'm going to use actually, let's use R as my 2. So that's -2 minus 2. So that's -4. And our X's, that's going to be that's going to be 6 minus -4. So that's going to be -4 over 10, which is -2 over 5. Right? And if you're comfortable with it, this is kind of like easy to say, right? The thing is, can you flip them or flip the fraction and make it negative, and so let's see. One fraction flipped and negative equal to the other fraction? That's the question. Right, so we can go to these two here as our answers. Right? When we compare them, is one fraction flipped and then one of them is made negative when the other one's positive? They can't both be negative, they can't both be positive. Okay? Awesome. Yes, they are. So we can prove it, right? So yes, QR and QP are perpendicular. Okay. So it's a right angle triangle. So QPR is a right triangle. Triangle QPR is a right triangle. Okay. Prove that the circumcenter is at the midpoint of the hypotenuse. Okay. So, oh, sorry, this is B. Prove the circumcenter is at the midpoint of, who's the hypotenuse now? It's PR, right? So let's maybe figure that out, who our midpoint of PR is. And we can talk about this. These kind of two questions are, what's the midpoint and what does it mean to be the circumcenter, right? So here, let's pull up our definition of circumcenter, orthocenter, incenter, centroid, all those things, right? This is okay, this actually I don't think is too bad. It's actually horrible, but okay. Let's do this. See if we can get a good one here. Boom. Where are you? Is it here? Ooh, this might work. Yeah. Okay. So we're looking for the circumcenter. Okay. So these. Uh-oh. Give me a sec. Actually, let's see this. Reopen the programs. Boom. So the circumcenter uses the perpendicular bisector. Okay. The centroid uses the point that connects the midpoint and the vertex. This is perpendicular from the midpoint, okay? And the orthocenter is the perpendicular spot to the corner, okay? So the perpendicular bisector, this maybe actually isn't, yeah, these are better. these are better. Okay, so let's actually use this. Come on now. We're getting there. Okay. So the medians connect the vertex and the midpoint. Right? The angle bisectors connect the vertex and the wait a second. Angle bisectors? Okay, I don't know what those are actually. Perpendicular bisectors we know of. Okay, so perpendicular bisectors are the midpoint. So this is perpendicular. Let's just maybe use that word. And the midpoint. And here, your altitudes are your vertex and your perpendicular. So really, it's just a lottery of vertex, midpoint, perpendicular, and each one of these is 2 of the 3. Okay? So what we're looking for, so this here is our circumcenter. This is our orthocenter. And this is our centroid. I believe that is the case. Confirm that here. Yes. Yes. And these, your angle bisectors, are halfway on each, so these angles are equal. Okay? Angles equal, and then just vertex. Okay? And that is called your in-center. I don't think we learned that one as much, so, but okay. Cool. Well, so that's our circumcenter. So we're going to need to find our perpendicular bisectors, or play with our perpendicular bisectors, and prove that it's the midpoint of PR. Right? So we actually should use the midpoint in our, kind of connecting these lines. So what that means is that this is happening like on the edge. It's both the midpoint and the circumcenter. The circumcenter is happening on one of these edges, right? Well, this is what happens with right angle triangles. This is just what happens because we have to go from our vertex we have to go, from our midpoint, right, to perpendicular from that, right? Well, okay, let's see it. So midpoint, and midpoint, right? And we have to go perpendicular. Well, this is the thing, is that we should always be able to create a little rectangle like that. And you have your intersection point of the 3 lines. Technically, this line is like just itself, but that is the midpoint of PR, right? So visually, we could sort of see it, right? So let's actually maybe just do this. And that is the Circumcenter. Okay. And it's the midpoint. Okay, so if we want to, we could maybe prove it. Yeah. Oh, wow. The chat is heating up here. Thank you very much, Beppa and Alice. Bumyo and Vored. Okay, some dueling, some interesting thoughts there in the chat, you know, some contradictory views, some opposing views. We'll see how it plays out, you know. Okay, we're done that one. We got one question left, folks, and we're going to take a little break. Food break, some tofu, some brock, and then we will be back at it. Okay. Back at it with the white bands as well. Mistaken for having you a heart would break your honor. I'll be around. It's your brother move. Bottle. This time I'm mistaken for having you a heart breaking up and down, up and down, to the bottom every battle. These still words in my head. We haven't done yet. No. I like you didn't know that. Been as a poor man feeling, and this is how you remind me. Alright. Good. Cannon launches a ball. A cannon launches the ball into the air at an angle of 30 degrees to the ground. Okay, so I'm already starting to draw here. Come on. Cannon. Shooting a cannonball at an angle of 30 degrees. Let's make it a big green cannonball. Okay, shooting at an angle of 30 degrees, sure. To the ground, okay. So let's just say this is a perfectly submerged cannonball. Yeah. There's a wall 200 meters away that is 200 meters high. Okay, so not to scale, but 200 meters high. And 200 meters away. Oh, careful, wait. I don't want to put it like distance of the spot that it was shot. Okay. Okay. Boom. Okay, so let's just stretch both those out. Okay, that's fair. Okay, cool. So that's 100 meters, and that's 100 meters. Actually, let's do this. It was shot. Boom. That's a little more fair. Boom. Okay. What velocity must it be launched at to just get over the wall? Okay. So maybe the way I've drawn it doesn't look right, but if I sort of like, you know, do this sort of thing, maybe we can make it look like it's going to get over, right? Okay. Beautiful. So the question is really, right? So this is kind of what's given. And what's asked is, what is the V1? Right? What is the velocity that you send this thing off with? Okay. Let's do it. So we've got to well, let's assume it says it just gets over the wall. So let's assume that we kind of catch it at that spot, right? So what that means is we now have a 1 spot and a 2 spot to look at. Okay, so that's what V1 is pertaining to, right? That's the 1 spot. And the 2 spot is going to be at this spot, right? So we don't, or let's maybe kind of ask this question. Do we know anything about it? So do we know how fast it's going there? Well, I don't think so, because if we knew that, we would maybe be able to get that a little easier. Do we know the height that it's at? Yes, it's at 200 meters, right? And now we've made a subtle choice there. What we've said is that this is your 0 marker. That's where I sort of start my measuring tape, and it goes to this, 200 meters. Well, what that means is my H1, right? So for the 1 spot, we now have said that H1 is 0 meters, right? Okay, so let's maybe just do this. Let's call that 2. Let's do this. Say 2 and 1. Okay. So this is the 1 spot. This is the 2 spot. Boom. Okay. The 1 spot, it's 0 meters. The 2 spot, it's 200 meters. The distance is 200 meters away, right? Well, that means that we've now chosen that this is my marker for 0 meters, right? Okay, keep going here. Do we know anything about, oh, we don't know V1, right? Okay. Do we know anything about the acceleration? Well, I want to ask about AX and AY. Do we know about any acceleration in the up-down or any acceleration in the left-right? It is not fair to say that there's acceleration in from the cannon. We're talking about after that 1 spot there, right there, is at the moment after it gets out of the cannon. Okay, so the cannon isn't doing anything to it. Okay, it comes to and it's in the air and it doesn't even, it just sees the cannon and says, did I come from there? Right, doesn't even know. Okay, so, okay, let's see it. The acceleration in the X is 0. This is really important. The acceleration in the Y is just gravity, right? It's just gravity doing its thing. So that doesn't really depend on 1 and 2. It's true the whole time, okay? So now let's actually compare. Let's, turn these into X and Y comparisons, or X and Y sort of distinctions. And so V1X, we don't know. V2X, we don't know. But they're actually the same because AX is 0, right? And X is the D. So D1 is 0 and D2 is 200. Oh, not 220, but 200. So X only cares about the D, and Y cares about basically the same thing, but in the Y. So they look very similar, but they're V1Y and V2Y and AY. And so AY is not 0, it's negative 9.81. Now we've kind of made this decision earlier, really, when we made our first decision about 200 meters, but this is something to sort of highlight here, that we've made a choice. Come on, mate. Let me just... I have to start a new page. I think it makes sense to start a new page after this anyway. Okay, so yeah, we might have to make this distinction, but we've already really done it, but we're going to say, I'm going to say up and to the right is positive. So that's why down is negative here, right? So negative 9.81. Okay, and we went up and to the right in both cases, so that's why D2, but this isn't D anymore, this is H, right? Because we're talking about vertical things, okay? And so both of them also have delta T. Time doesn't care about X and Y, they're the same thing, okay? And we don't care, we don't really know how long it takes, right? Okay. So what do we know here, right? This is tough because we don't know the time, we don't know the velocity, so we can't really use the distance that it travels, right? Or at least that's stuck in an equation with two unknowns. And then here in this world, we actually need 3, so delta H doesn't count as one of them. We are going to use this to get to delta H, but that's only 2 of the 3 that we need. We need either V1, V2, A, delta H, or delta T. We only know A and delta H. That's only 2 of them. Okay. So what we're going to have to do is we're going to have to set them up so that these two things actually are related to each other by the triangle that they came from. Okay. So let's clarify that V1 vector has a V1x and a V1y, okay? And those come from V1 times the sine of 30. Right, so I can, you know, put that there. That's the same vector as that, right? Okay. Times the sine of 30, and this is V1 times the cos of 30. Okay. So we don't really know what they are, but we can at least put them both in terms of V1, and now we can start to smash these equations together. Okay. So let's do it. So V1y we now know is V1 times the cos of 30. Okay. And V1x, oh, sorry, that's V1y. So y is the sine of 30. And V1 times the cos of 30 is the V1x, okay? And that's actually the same as V2x. It's the same. It's the same because it doesn't change. Okay, but for now, let's just ignore those because we now can sort of use this to come up with the equation for time, right? We can now say that V x is delta d over delta t because this doesn't change. The acceleration is 0 this whole time. So delta d is 200. Delta t we don't know, but Vx we sort of know now, or at least we can sort of rearrange this. So let's not say that. Let's say delta t is equal to delta d over Vx, which is V1x and V2x, because it's just the same velocity the whole time. Okay, so then 200 meters all over V1 cos of 30, and now our delta t is something that we can kind of come over here and pretend like we at least have one of them. So 200 divided by V1 cos 30, and pretend like we at least have one of them, right? Because now we have 1. Delta H, remember, is just 1, so these two contribute to delta H, so that's 2, and now we have 3, and so we can solve for this one, right? Okay. Another thing we could do is we can also kind of like pretend like we have this one now, and combine it to find delta t as well. So let's actually do that, because then we can solve both delta t equations or set them equal to each other. Okay, so let's now pretend like we have enough here, pretend like we have enough here, and we now have 1, 2, 3, and we can solve delta t. Okay, so what I see is v1 a and delta h. So this is going to be a delta h is equal to v1 delta t plus 1/2 a delta t squared. Right. Okay, so this might actually be pretty ugly, because we're gonna have a delta t in both terms, right? Okay, so let me just kind of like quickly do the solving that's necessary here. It's ugly, but we're almost there. And we will take a little break after this. Okay, so then that times delta t, which we're just going to say is delta t for now, plus 1/2 negative 9.81 is our acceleration. Delta t is just itself for now. Okay? And so we need to solve for delta t, right? Well, we're going to actually just need to rearrange for delta t by completing the square. Let's not do that. Let's just sub in our delta t into this equation. Okay? So we end up with 200 is equal to v1 sine 30 times delta t, which is 200 over v1 cos 30. And so now that cancels nicely, plus 1/2 negative 9.81 times 200 all over v1 cos 30. So this is sub into... Alright, that's what we did there. And, sorry, that's squared. Alright, okay, so let's do it. So this is 200, and now what's nice is these cancel. And so then this is just the tan, right? Because this is the sine of cos. Sine over the cos, which is the tan of 30 times 200 minus 4.9. And this is for... okay, so this is 5, 3, 3, 3, 4.3 divided by v1 squared. And now we just have an equation where we have to solve for v1. So we just have to get a v1 out of this. Right? And we've solved for the v. Okay, so let's do it. So 200 minus tan of 30 times 200. So 1 minus the tan of 30. So that is 84.53. And let's just make that negative so that we can just 4.9 times 5, 3333.223. So that is... Wait a second. Hold up. Wait a second. How is it that that is... Oh, you're right. Fun rent. I didn't think of that. Okay, thank you. Wait a second. Wait a second here. Wait a second. Wait a second. Bum, 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 bum. I'm not sure. I'm not sure. Not sure what the issue is here. Seems like my negatives are going to be a problem. Right? Right? Is that right? I think that's right. Squared equals a negative. How is that the case? It's traveling up. Yes. That's going down. Yes. Divided by velocity. X is cos 30. Yes. It's 200 meters. Yes. 1/2 a delta t squared. Yes, that is the equation. Excuse me. Excuse me. Hey, relax. Nice. Nice. Good stuff, Samuel. What is the issue here? Delta T is going to be... Where's going to be a negative velocity? No. But negative value there. Okay, is that a vertical velocity? Yes. And so it should go down. Right. 100. Yes. Yes. This is all correct. Right. It's the sum 30. 30. is this? Possible. What is going on? Finalize the initial positives. Yes. Time, yes. Yeah. 1, y is sine. That's what we used. V1, y. So, what did I get wrong? I mean, this doesn't make sense for me. Right. Right, because this could be positive, this could be negative. I mean, isn't this just wrong? Let's do this. Put that there. Remove that. Put that there. Just do that there. Make all of this smaller. So that. Alright, that was the 2. Okay. Sure. Okay. So 9.1. Okay. I'm not sure. I screwed this one up. I gotta come back to this one. Alright. I'm gonna take a little break. And we'll be back. Time. Let's actually something.
Make a little tweak there then. So label your, you have values for your FTY or FTX yet? Analysis is like something small that burns you here because you've gotten every step. You have values for your FTY or FTX. This is the kind of like chemistry question that would not. And so have you tried this one? Okay. Yeah, this is definitely a interesting one. Okay. So, and so have you tried this one? What's your sort of status on exposure to this one? Just sort of taking a look. Okay. Okay. So let's like this, even took me a kind of second read to even see what was going on here. So let's take a couple reads, see what we can get out of their question into our sort of givens, and maybe if we can find a crumb trail, or maybe we can at least see something that we can, that looks familiar that we can kind of like get some more information on, a free body diagram, or start to explore a bit. Okay, so I'll give you a minute here, give it a couple reads, see what you can highlight. Okay, okay, we got that they're neutral. Okay, so you've got more. What's the setup here? Is there strings? Are they hanging? What's the deal? Okay, so we've got sort of like how many spheres? Two spheres. Okay, do you know how far apart they are? Are they touching? What? Okay, good, nice. I like it, even converting that. So 0.15 meters between them. Okay, I like it. And they're neutral. Yeah. Yeah, the mole of carbon, it looks like it matters. It doesn't. It doesn't. If I just told you a sphere contained this many atoms or this many electrons, that's what you could do this entire problem that way. You wouldn't need a mole. The mole there. But if it was needed, it would be extremely unfair and it would be fully a chemistry question that would not pop up here. So it's almost unfair to give you everything you need to know about the mole because it's a whole concept. So they won't really do that. Like it will be it'll just be a smokescreen. You can do everything without it. Okay? So we know how many electrons are in each, right? Can I ask you this? What what do they ask for? What will our answer be? Yeah, yeah. Mm-hmm. Okay. For FQ to equal FG. Yeah? Well, ooh, okay, okay. So this is more so a problem with, so first of all, is there an FQ? Is there an FQ right now? One word that you can point to say yes or no. No. Why? Neutral. So if they're neutral, they don't have an FQ. So it can't be equal to the FG, right? Can I ask you, what FG is this? Is this MG for each of them? No. No. Because it doesn't just say their gravitational force. When I say gravitational force happens between how many things? Two. If I just say gravitational force, you're safe to assume who the other gravitational force is. The Earth, right? What is it? Yes. Absolutely. Yeah. Mm-hmm. Mm-hmm. Yeah. Okay. That sounds like a pretty good crumb. You found half the loaf there. So let's follow it. Let's follow through with that. Okay? Like yeah. Yeah, I mean, and this is one of those things, right? Where like the only word that I could really point to is that to say no, no, right? And this is again like that last one. The word equilibrium was like the whole problem, right? And so sometimes it does come down to those one word things, right? I so first of all, to say it's sneaky, I kind of agree with you. I kind of don't. It's sort of like, the student in me agrees. The teacher in me says that it's it's our job to sort of like show you the tricky ones because the easy ones are going to be easy, right? Like that's kind of the trick. That's the problem of the relationship of kind of like presenting problems. You're never really going to get to the point where you're just doing problems that you feel really, really good about for hours and hours because that's a waste. You want to be putting that time into challenging yourself to learn more, right? Like it means you've learned that concept pretty good. But what that means is that you are always in this state of like, oh, just grasping and all this stuff, right? Which really puts the mental stress of confidence and all that relationship into out, right? So, okay, anyway, sorry. Enough of a rant there. So, you have a crumb. I'm going to leave you here. See if we can get to, and we don't necessarily have to get to a fraction, but even just sort of like something about the electrons, right? Okay, get me there. Mm-hmm. Good. Yeah. Doesn't even matter actually. Okay, so you got that that their equations kind of get to this point, right? You got to this point. Right? Eh? Do we know anything about um okay, so you canceled the R's, yeah? Okay. The K's and the G's are gonna kind of work themselves out, right? Like they're just numbers. But what about Q1, Q2? Are there different charges or the same charge or what? Yeah, spheres are identical. Good. So we can sort of say K Q squared equals GM squared. Okay, do we know the mass? Okay. Yeah. And they're asking what fraction of electrons would have to be transferred, right? So that's kind of like do you agree that the equation to sort of figure out the fraction, let's say we figure out whatever the charge is, right, that of the thing, then it's going to be over the total charge of like all the electrons. Do you agree? Like those are the number of electrons that left. It will be, but to do that, we'll do a division of, something over the total. That's how you find a sort of what fraction of the total, right? Okay. So I'm just sort of like qualifying that that's what we're gonna figure out right here, right? Okay. What that means is let's um I wonder if we could sort of like say if we knew that this was all of the electrons, let's just assume that all of the electrons went, we could figure out what the mass was, right? No, but then it's okay. So I'm trying to do this without the chemistry. You actually could do this very easily with the 1 mole of carbon, which is the problem, right? So yeah, I don't think it's going to either. So okay, so let's see if maybe there's something else. Yeah, yeah. Yeah, I mean, we kind of already did combine the equations, right? So like in some sense we are using the two equations there. We did also, like technically we could say that we're doing like this, right? And actually, one is negative of the other, right? Do you agree with that? That one is negative of the other? One of the... So if they're electrically neutral, then one loses electrons, the other one has to gain electrons. The one that loses electrons is now positive or negative? One that has lost electrons. Yeah, so now we have a positive, and then it gave its electrons to something else, which now has extra electrons, so that's negative, right? So if this thing does this type of transfer, right, then this is now positive. This is now negative. Okay. Yeah. Yeah, because we're transferring electrons from one to the other, right? Um, but yeah, I'm very tempted to just sort of, I mean, because this is actually the definition, which is, does make me maybe think that it is the case, because the definition of a mole comes from carbon, but 1 mole of carbon is 12 grams of carbon. Like that is, that's kind of where a mole came from, in some sense. So if that was the case, then we could use that in our masses, and now we could solve for Q, right? Yeah. Yeah. It's definitely like a little unfair. I'm just trying to think if there is any other way that we can kind of approach this. Um, go ahead. I think honestly, like this is how I would do it. Generally, also when there's a fraction idea, we can get away with saying we can do like a sort of like division of one equation by the other, if that makes sense, right? So, okay, so check your formula sheet then. Maybe there's actually this on your formula sheet. Is there a gram per mole mention on there? No? Okay. Do you have the elementary mass or mass of a proton, mass of electron? No? Wow, that's a little strange. Okay, so that means you're probably not going to be doing an oil drop experiment, which is interesting. Yeah, yeah. You did do that? Okay, interesting. Oh. Yeah, I mean that's pretty close, right? An atomic mass unit. Yeah, like I would be interesting to see it because like and like, especially once you have the understanding of this, it's like, oh my God, this is so easy. I don't even want to try to do this another way. It's just like once we have that, we have the mass and we're good, right? So then we would solve for Q and then kind of like divide it by that to figure out the fraction, right? It is interesting that they give us this distance when we don't even need the distance. Oh, you have his solution? Awesome. Okay, cool. Yeah. Okay. Yeah. And he might have sneakily done this, like There's actually a few different ways that I could kind of like sneak this into the question without actually saying this about carbon or about 12 grams or whatever. Could have also, so I don't know if you've done mass charge ratios, right? Like mass spectrometry. I don't think you've done that yet, right? You haven't done magnetic fields yet, right? Okay. Okay, so that's when you'll do magnetic fields and mass spectrometry. I always have trouble with that one. And that's when you'll talk about mass to charge spectrometry. Yeah, it's hard. Okay, did it send? I didn't get anything. Let me refresh. Oh, there we go. Wait. Oh no. Oh, okay. It came and went away. Okay, here we go. Yeah. Right. He used he used 0.012 kilograms for the masses. So that's 12 grams. He just snuck it in there. Oh, that is sneaky. Yep, he did this. He used it without even telling you. Yeah, he just snipped it in there right at the last thing where he solves, where he plugs in m squared there. You see it? You'd never know. Yeah, exactly, right? Yeah. Yeah, I know. Show your work, eh? Where's that mass come from? Yeah. Yeah. Okay. So he kind of like threw this all into one equation, right? So I just kind of want to show you that method too, where like whatever charge you get, it's going to be some multiple. So that n is either like 1, 2, 3, 4. It's not 1.5. It can't be 1.5. You can't have 1.5 electrons, which means you can't have 1.5 charges of an electron, right? That's the charge. So every charge that we see in the world will be a multiple of the electron's charge, right? Does that make sense? So if you see a charge of 2, that actually means 2 electron charges, right? It doesn't mean 2 coulombs, right? Because coulombs is the unit of charge. But when we say like a calcium 2 plus ion, right? I'm saying the charge is 2, the n value is 2, and the E is the electron's charge. Do you agree with me? Do you agree that I can't have less than the electron's charge? Yeah, like if I tell you that there's an ion here, you say, well, it's either a plus one or a minus one then. It's not a minus a half or a plus a half. It can't be, right? And that's what the one and the two and the half and that we're just saying, that's what that references is how many electrons have been lost or gained, right? It is kind of a constant. That's why it's called the elemental charge, because it's kind of like some like fundamental idea about the universe that like every charge you see will be a multiple of this value because this is the smallest unit of charge that we have. Right? Okay, so then yeah, so then he just throws this in for Q and now it just kind of rearranges and what? Yeah, that's what we're just saying now, right? It is measuring coulombs, but it could be just how many electron charges do you have? And that's what n is. How many electron charges do you have? If n is 5, then you have 5 electrons charge worth. You just use this equation and subbed it right in for Q here, and so we ended up with n squared E squared. And now what's nice about that is n is going to be a nice number that we can solve for. E is a number that we can use our formula sheet for and just plug in as a number. Right? Yeah, that's cheating. He didn't even mention it. Snuck it in there. That's almost slimier, right? Because it's like it's not even going to mention that they need to know this. So yeah, so he does this and then he rearranges. Oh, and says, we're really solving for n, or n squared at least at the start, and so it's gm squared over k e squared, and then we square root that. This will be the number of electrons, right, that have in the charge, right, causing charge, or you know what I mean by that, right? And then that we will compare to our starting value of how many we had here, because that's the total number we had. This will be the number that kind of got transferred, and then we'll come up with a fraction based on that, right? So the fraction of electrons. Yeah, it's a little sneaky, right? Yeah, I think that would be a strong hint too, right? Like you would go from there when you got to this stage and you're like, wait, I don't know what m is. You wouldn't have gotten to that point without knowing what m is, and you say, oh, I know m. G and k are both constants. I can find out what q is. Now I have a crumb to get, the fraction. Right? Yeah, that's frustrating. But I mean, it's good. So what I'm here for, right? Like that was kind of our suspicion, and otherwise we wouldn't have known that, right? Okay, cool. So let's see if we can try one more before we go here. That's okay. Yeah. Maybe like more of a communication type question too. I feel like we haven't like remember we kind of have to hit Kika, right, on our test. Knowledge, inquiry, communication, application. The tough thinking, the strange, the weird questions, like that one was a thinking question. The knowledge ones are just like testing your straight kind of like formulas, nothing too wild. Um, Inquiry is generally like a little tougher, the thinking inquiry ones. But communication is a whole section of like graphing and writing, like definitions and telling like what's, like what. Really? Oh, that's nice. So when you like, do you get on your test, do you see your breakdown of Kika? Oh my gosh, it's so annoying. Oh, oh, just feeling. Sometimes, right? It feels like that. Yeah, yeah, yeah. Uh, rereads the whole thing is wrong. Wow, that's yeah, I mean, I didn't know that they could do that. I thought they were kind of like restricted to use Kika because I think I don't know if this is true, but I think it's like your right to know where you're getting your marks from, like something that they did to like so that teachers don't just kind of do what you're saying and just be like, but I think it came from like teachers being like, I don't like this kid, I'm just gonna like make up that they did bad or mark them harshly, right? So I think that's part of it, right? Okay, that's probably where your knowledge comes from. I don't think your communication would come from there, really. Like communication, yeah, would come from like anything that you're like writing an answer rather than like doing math for the answer. Really? Oh my gosh, he's cheating you. It's generally good because those are usually a little more boring and a little more like theory based stuff, which isn't as nice and fun. So that's okay. Hmm. Right. Okay. Yeah. Okay. Interesting. Ooh, projectile. Okay. Oh yeah. Yeah, this is definitely a question type that you should kind of like get comfortable with and be ready for. So we can kind of like take an energy approach to this as well as a force approach to this. Okay. Um, mm, okay, that's nice. That's valuable to have. Okay. So let's sort of see this problem. And you said it's a projectile motion problem, right? And it looks it, but how do you know it's a projectile motion problem? How do you tell if something is a projectile motion problem? You know? Okay, so it's got that certain look of the like parabola, right? And that's it. Yeah, exactly. Okay. So they tell you a few things here, right? They tell you um the electric field strength, right? And so that's 0 times 10 to the 5. And can I ask where is it that value? Because generally we kind of point to a certain spot and say say the electric field is this. Where is it that value? Yeah, in between the two plates. So this is the thing about these two plates like this. They set up a perfect uniform magnetic field in the middle where anywhere in this box, the value is that amount. It doesn't matter that I'm closer to it here or here. The value for the magnetic field is the same no matter where I am in this box. Okay? Okay, well that's a lot like the box that you and I live in gravity, right? Where no matter where we are on this planet, we feel the same force, right? Well, this isn't quite a force yet. How do we make this a force that affects the proton? How is FQ related to electric field? What unit am I asking you about? I'm asking you about the unit of newtons. And the unit you have is newtons per coulomb. So what do you need to find newtons? The number of? Yeah. So this is just Q, the charge that's experiencing it, times the magnetic field that it's experiencing. Yeah, that's one of your formulas, right? Okay, so then where do we go from there? We have a force now, kind of like the gravitational force, right? Okay. Wait, what Q would we use there? Yeah, the positive elementary charge, right? Good. Okay, so then where do we go from there? Have an FG. Okay, let me take you out of this unit for a second. Let me tell you that I've got a cannon, okay? Your old friend, right? And it's going to shoot a ball off of a ledge, and we're going to catch it 12 meters later. And I want to know how far It's fallen. What do I do? And I tell you that the velocity here was, don't look, 1.5 times 10 to the 7 meters per second. And this wasn't 12 meters, it was 12 centimeters, right? So let's just tweak that. Okay, so what would you do in this problem? Yeah, but this is the projectile motion back to kinematics, right? We have to do, yeah, yeah, V1, V2, A, delta D, Y, right? These are Y, V2, Y, and then delta T. Okay, so let's go from there. What do we do? dy, yeah, delta dy, right? Okay, so we want to solve for this. Do we know A? Not quite. We don't know G, right? It's not G. It's not G. No. Well, it is, but this could be the vertical view, and this could just be moving to the right, and my two horizontal plates could be like held vertically, and I could be looking from this angle. Do you agree? So in that case, then we don't have to worry about gravity, right? Okay, so then what is the acceleration there? What's causing an acceleration? There, there must be an F net. Newton says there must be an F net if there's an acceleration. And where's the F net? Who is causing an unbalanced force? FQ, yeah, FQ, the force, FQ, right? So then we can solve for, um, no, no, yeah. So we can say FQ is equal to F net, which is equal to MA. And I think honestly, you're gonna have to use the mass of the proton. Okay. And then we can solve for acceleration. And then what? Yep. Yeah, and actually time's gonna be the connection to get us to the x. Because we know Vx, and do we know delta D actually? Delta dx? Yeah, we know it, 12 centimeters. So we can actually find delta D that way, right? So, okay, so yeah, we can solve for delta D, plug that in now. Now we don't have to worry about it, and then we can use that to solve for no, delta dy. Okay. For this one, yeah, in the x, yeah. dx is equal to delta dx over delta t. We'll solve for delta t. I'll sub it into the y, and then solve for delta dy. So that will be delta dy is equal to v1 initial delta t plus 1/2 a delta t squared. What is the v1 initial? Yeah, it's vertically, it's not traveling any speed at start there. So that's it. Yeah, and your time. That's it. When the oh yeah, all the like the earlier unit you mean. I thought you meant like the dimensions, the meters, the seconds. No, but the yep. Kinematics won't ever go away. That stuff is like something that we can always pull out because speed is a connection, and then we have energy, right? And energy is always connecting to everything. So now we can go back to kinematics through speed. And now this is energy, so energy's everywhere, and so we can go back to kinematics. Yep, this is definitely like the type of question that you'll see, and it won't necessarily always be kind of like like a kind of perfect case like this. It might be an energy scenario where I'm kind of asking like, how fast is it going here versus how fast does it leave? Well, then it's just about how much energy did the plate give it, right? Yeah, then I would do the energy approach. I wouldn't care about kinematics, right? So you got to kind of ask that question of like, what's gonna get me there, right? Like here, the delta D there is restricting you, and like V and delta D, that's calling out for kinematics, right? But if you don't have to, use energy first, and then if you have to, use kinematics. Yeah. Okay, cool. Good work tonight. Um, okay, do you feel like this is like coming in a lot more like solid? It's sort of things you're getting ideas of what to do as you're kind of going through the question. It seems like as we go through the question, like you're seeing the layers as they're getting peeled back, like a lot faster, a lot easier, a lot sort of like there's a lot more transparency to those layers, right? Where you can see a few layers deep now, right? Which is a big part of physics, right? Knowing where you're going. Okay, awesome. So I'll send you our note from today. Is there anything else that I can get you? You looking for extra practice problems or anything in this stuff? Yeah? Okay, I can get you some, absolutely. Hard or easy, but just not what he does, not what he uses. Mm-hmm. Hmm. Okay. Okay, so let me just make a little note. I'm gonna send you some, okay? Yeah, no problem. Um, status. Okay, cool. And I just wanted to check in, like, do you have an idea of a test on the horizon? Yeah? Okay. So then what do you go ahead, sorry. Okay. Okay. Right. Yeah, Waves is actually a little bit of a shorter section, but there is some crazy stuff that happens there that will well, so I mean, this is something that you will talk about, but light, so you've talked about electric fields, right? And a plate like this, you can imagine if I hooked up, so do you know what alternating current is? You've heard that term before? Okay, and you've heard direct current, yeah? Okay, direct current is just like a think like a water tap when I turn on the tap and water comes out. Direct current is that, but with electrons. Like instead of water molecules, it's electrons coming out, right? And so the thing that matters is that it's a bunch of charge coming out, right? But it's like all charge just going in one direction is just like a big hose of charge, right? And so it kind of like builds up and builds up. The problem with that, it gets dangerous if you like accidentally kind of like there's a leak or something, it'll just like keep going, keep going. Okay? So it's dangerous. So anyway, everybody uses alternating current now, which fluctuates, and your it's basically like the positives and the negatives of your plates here, they constantly like switch back and forth, so that the electric field is like up and then it's down and then it's up and then it's down and then it's up and then it's down. So it's kind of like I go with the electrons, I go through the circuit and then I come back with them, and then I go through with them and I come back with them. Well, what does the circuit feel? Electrons coming through it. It doesn't care that it's one direction or the other. Okay. Okay. So just to our point of waves having to do with magnetic fields. So light is actually, it's a fluctuating electric field. As it travels in the space, in that little box of space that it's traveling through, if you were an electron in that space, you would be attracted up, and then you'd be attracted down, and then you'd come back to normal. And that's what you would experience if you were an electron. It's kind of like if you were in the water, if you were a beach ball, you go up and then you come down, and then okay, now that wave just went through me, right? That's one part of light. The other part of light is a perpendicular. So electromagnetic field is going up and down. Sorry, electric field is going up and down. Magnetic field is going left and right. Okay? And that is what light is. That's what light is. Like, we don't know what's going on or why it's like that, or, like the why is not really for us to answer. It's a perpendicular. So can you see it? Like the orange one is meant to be kind of like horizontal compared to the, right? Can you see that? Like this is meant to come out of the page and then into the page and out of the page into the page, right? So that's what light is. It's a fluctuating electromagnetic field. Have you ever heard of the electromagnetic spectrum? Electromagnetic spectrum is the spectrum of light. That's what light is, right? So, wow, it's crazy, right? Like, I don't know. Like, light is definitely a strange thing. And you're actually going to learn a lot more of the strange things about light. And in fact, because of the strange things that have to be true about light, there's strange things about us that we just don't notice. Like we are always vibrating. Like every particle is always shaking just a little bit, and you could figure out, but we're just so big that you can't notice it. But little tiny particles like electrons, you can't quite nail them down. You can't say that it's exactly here. You can't spot them because they're too, yeah. It gets weird, okay? And it'll get weirder. But for now, that's the kind of relationship, okay? Okay, cool. So,